So these are now common pitfalls. As I remember, both inside and outside meteorology. And in these books, in particular Kahneman's, they list overconfidence as a general human weakness in politics, economy, military matters, and as we have also seen in the verification of probability forecast, also in weather forecasting. We tend to be too sure about a lot of things. And when they ask, for example, people, do you think you are better than average car driver? 80% thought that they were better than the average, which is, of course, a mathematical impossibility. So if we have 3 forecasts from 3 different models, and they all show it will be dry. Test which we made, I think at the Met Office, showed that there is still a 10% it will be rain, which can also be understood that it is just through a 3 model, so it's not a great ensemble. But if you have the Met Office, European Center, your own model, or and they all are dry, it's a strong case to forecast unconditionally dry weather. On the other hand, if all these models have rain, then we must say, it will surely rain, but it will only rain in 80% of the cases. So this is one source of overconfidence. We draw conclusions from too few samples, and by the way, they are also, as with all NWP, correlated. They are not independent, these forecasts. Even if they come from different models, they rely on the same data. And so it's... then I repeat this diagram. Not the typical, but the average behavior of a probabilistic system. You start from 10 days before the event with very low probabilities, and on average, not every day, but on average, they increase slowly, but at any stage, they are of course free to back out. So even if you have reached now 90% probability the day before, there is still a 10% chance that the event will not happen. It might go back to 0. And that is obviously what happened in the New York case 10 days or 2 weeks ago. So even so, one can never be completely sure. And I mentioned verifications, and this is a it's a reliability diagram with the forecasted probabilities on the x-axis and the observed frequencies on the y-axis. And ideally, the forecast should line up along the 45-degree line, the diagonal. But typically for subjective forecasts in the 50s, statistical interpretation schemes in the 70s, 80s, and also for the EPS, is that there is a slope of less than 45 degrees. It means that it forecasted 0, but still things happen. It forecasted 100, and it does not always occur. So overconfidence is a common theme in many forecasts. Then we have the halo effect. And this slide was made at the Met Office. So you have 3 models of equal quality. They should be judged objectively. But if you're at the Met Office, then of course the Met Office model stands out. It has a halo. If you're in the European community, it might be the ECNRBF model. If you are an American, it might be the American model that you emotionally attach more value to. And as some sort of proof of this, before the European Center, the Scandinavian countries relied on Washington, Bracknell, and Offenbach in the 1970s. And we had Nordic meetings, so we traveled around and we learned from each other. And then it was odd to find that the Norwegians forecasters favor the American NWP. And the Danes were favoring the Met Office. Perhaps because there's a lot of trade between Denmark and England with butter and ham. They favor the Met Office model. And Finland, who was aligned with Germany during the Second World War, they favor the German model. I don't know exactly why, but they had different, and it smells a bit like reminiscences from the Second World War. And during that war, Sweden was neutral, and consequently, we relied on all three models. So this might be an example of the halo effect. But I'm sure there are more. Also, you can scratch your own souls with respect to the Cosmolabs system. And then we have the representative effect. That is, in Kahneman's book, Kahneman might be a male chauvinist pig, because his example is with Linda, a feminine activist. And I don't want to use that. So instead, I took rugby player. So here we have whatever his name, and now what is more probable? And this is a Linda syndrome in the scientific books, but I don't want to be male chauvinist pig, so I took what is most probable? That Danny is an accountant, or Danny is an accountant and a skillful rugby player. And you see he has a lot of muscles. And in the corresponding Linda question, 70% thought that number 2 was more probable than number 1. And perhaps you would also do that, considering his muscular nature. However, this is completely illogical, because being a rugby player and an accountant is a subset of being an accountant. So for pure logical reasons, it's more likely he's an accountant after all, even if he doesn't look like an accountant. He more looks like a rugby player. And then we come to, and this is a very common problem in life, and that is what I have mentioned before, to confuse the typical with the probable. Of course, he looks like a typical rugby player, no doubt about that. But it's not the same as probable. So, and then we also have the problem with the base rate. There are much more accountants not being rugby players than accountants being rugby players. So there is also this problem that we tend to over, just because he happens to look like a rugby player, does not mean that he is a rugby player, because there are very few accountants playing rugby. But still, with the Linda problem, which is sort of similar to this, 70% answered yes to the second alternative. So typical and probable should be separated. And more about typical and probable, a very common misunderstanding in lottery or is that, for example, if you throw a coin, you can have this head, half head and half tail, and then a mixture, irregular mixture of head and tail. And then you ask people, what is more probable? And again, people tend to take the third as more probable than the two others. Although, of course, all three are equally probable. It's just that the third one looks like a typical random event. And most of these tosses lead to random series. So 99% of the sequences will look similar to the right-hand one. But it does not make this very sequence more likely than the two others. So again, we are easily deceiving ourselves. And it's called the representative. So it's this sequence represents random outcomes, but it does not mean that it is more likely than the two others.
Excuse me, Anders, but I have to make you a sort of frequentist question. So, we study in the book that the a priori probability for a coin is 0.5.
Yes?
Yes. So, in which way you can say that is equally probable?
That?
In which way you can say that they are equally probable? Because of the order.
Because
can you please separate the frequentist approach that
no, they are.
That the probability is of 5?
It's equally probable to have the first sequence, the second sequence, and the third sequence.
Because every toss is uneven.
They are independent. So if you now take 0.5 and multiply by 8 or
yes, but if
10,
if you try 3 million times that
yes,
at the end the probability to have the second one is higher.
no. If you throw now 300 million times, 300 million times or whatever, and then you will have, and then of course you might have these specific outcomes several times. But anyhow, whatever you do, you will have an equal number of the left, center, and the right. However, you will have 99.9 outcomes which look similar to the right-hand one, but not exactly. So if you have a lottery and you have to specify 8 numbers in your, if you write 7, 4, 8, 1, 2, 0, 0, 9, 5, or if you write 1, 1, 1, 1, 1, 1, 1, 1, both are equally likely to win. And the same is true here. These specific outcomes are equally likely. What deceives us is that the sequence coming up normally looks like that one. So this represents the sort of irregular outcomes, whereas the two others represent the few regular outcomes. And they are in minority. They represent perhaps just a promille of the outcomes. So we have the representative error again. This represents something big, but it does not make the sequence as such more likely. I'm happy you asked that because it confirms that we have a problem. Yes, well, not only you, Carlo, but you are brave enough to admit it. He admits his uncertainty, so he's taking impression of my course. And the same now is true, in my view, in meteorology. So why people favor the ECNRBF 10-day forecast in all its detail and beauty instead of the much more likely or probable ensemble mean is because the ensemble mean does not represent a picture of the atmosphere. The atmosphere never looks like that, but it can very well look like the upper left, and I have more examples of that. Here we have the European Center's fantastic graphical section that puts a lot of skill and energy into making wonderful portraits of the atmosphere. So this is really a typical image of the atmosphere. You can put it in a school book about the atmosphere. But as a 5-day forecast, it's rather useless because all these wonderful details do not exist or they are somewhere else. So the first, I have now list 5 mistakes because I'm not afraid of criticizing the ECNWF. So the first mistake is that they use skill and resources to draw on this misunderstanding, to increase the member state and the meteorologists' misunderstanding of typical and probable. So they make the sort of underpins this representative error by making these wonderful but not reliable pictures. And here is another example. We have to the left an interesting detailed picture of the atmosphere. Now this is the corresponding, this is a forecast, and this is a corresponding ensemble mean that tells you what you can rely on. And obviously this cutoff west of Portugal cannot be relied on in the forecast. That is what you get from this ensemble mean. You can rely on the low northwest of Scotland and some high pressure system to the east, but not, and some low south of Greenland, but not the Bay of Biscay cutoff. But that map looks much more appealing than this one, which perhaps is the atmosphere will never look like that. And that is where I mentioned yesterday about this new clustering, whether instead of putting the ensemble mean, the mean of the cluster, the mean of the cluster members, they have now taken the most representative member, the most typical. And then they are really playing on our misconceptions because, of course, these typical members look very realistic and some large-scale features are predictable, but they also contain a lot of non-predictable, nice features. So the UPSM is here playing on our prejudice. So my second criticism is that they take advantage of our human weaknesses. Then we have the model of the day, and that is also something because when our forecasters, meteorologists want a nice, realistic image, they can get that from one of the models, one of the members. So the problem is, as Stefano ridiculed yesterday, and I also ridiculed, to think that you can find which member in the ensemble that is the model of the day. And from my experience, I think that is possible for the first 12, perhaps 24 hours, when you can compare the first 6 or 12 hours forecast with more recent observations and see which models seem to be in tune with the atmosphere. Then you might rely on that model for another 6, 12, 18 hours perhaps, depending on the situation. But beyond 24 hours, it is in my experience and from other considerations impossible. So here we have, imagine now that we have 10 ensemble members, just to make it more treatable. Now can we judge here which one is the best one? And for another reason, that is this one seems to have succeeded best in the verification, but that might just be a random event, and the problem is, can we know that beforehand? But because how the atmosphere works, what influences this low over France for the first 12, 24 hours is what is happening upstream over Britain and a bit out in the Atlantic. And that is perhaps possible to have an opinion about. But if we go beyond one day, we have to take the whole North Atlantic into account, because what is happening there will influence France in 3 days' time. Secondly, what we normally look at is a surface map. But what influences is, of course, also what happens in the 850, 500, the jet stream levels. And we normally don't look on all those maps, and in particular not to see if the forecast is in line with the observations. In particular, since observations were made at 00, and we look at this in the morning, and the 12 UTC radiosondes or observation had not yet come in. So practically and theoretically, outside statistics, it is not possible to draw conclusions about model of the day beyond 12, at best 24 hours. But it still happens. So my experience tells me that this member is a good one, and then I have a detailed 10-day forecast. And those who claim that should be asked, can you please verify that your intuition and experience leads you right? So again, this about the best member or the typical member is sort of encouraged by this new clustering technique, because it seems to be able to pick out the best or most typical member. So I think that the European Center is not behaving scientifically in this respect.
Anders, concerning this new clustering technique, remember that he is picking up is selecting the typical member of a certain cluster differently at each time interval. So it's not keeping the same member for 10 days, but so it's slightly different from what you say in this sense.
Well, sometimes it can very well be the same member throughout, of course, but you're all right, it can be different. But it's still, yes, that is a small argument for, but it is not, in my view, decisive, because what the old clustering in principle presented an average of all the members. And of course, in the longer the forecast, the larger the spread, and the more smoothed, more averaged the field looked like. And it didn't look like the atmosphere after 6-7 days. But then the forecast community should have said, well, it's better that we learn to interpret those smooth fields than to force upon us these detailed maps which are not really relevant, because our fathers, our methodological fathers and grandfathers before the computer, they worked with 5-day average maps. So it was a common practice until the 1980s, when you make longer forecasts, to work with averaged 5-day or 7-day averages and see how these averages moved and try to extrapolate them. And for example, the Rossby waves, which you have read about, were discovered by Carl Gustav Rossby in the late 1930s, when he was actually working with 5 or 7 day averages. And he learned to interpret these sort of not quite physical looking maps in a physical sense. So that's the road the meteorologists should have taken, to learn to interpret these not quite physical maps instead of taking their 1-day experience and transplant that into the full 10-day, as if the 10-day forecasting was just a matter of interpreting maps as it is on the 1 day. Now, sometimes it happens that the 10-day forecast is perfect. And it happened in summer 91. I had just come to the European Center when the 10-day forecast was almost perfect, and even better than the 24-hour forecast. So it can happen, but of course it's very rare and it's nothing to speculate about. But unfortunately, weather forecasting today seems to assume that that it can happen often. Then the mean, again. And this is now a real case from the Eastern WF, where a scientist had a suspicion that the Icelandic low, that we didn't forecast the Icelandic low sufficiently deep. So it was a scientific debate in the European Center. Are we underestimating the intensity of the Icelandic low? And then he took many forecasts and averaged all the forecasts and found this result, the blue line, and compared with the analysis and draw the conclusion that we indeed are making the Icelandic low too weak. And so here, but this was another case of misunderstood statistics. Imagine now that we have, 15 forecasts of the Icelandic low. And to the upper left is the analysis. And as you can see in this case, all these forecasts have the right intensity of the Icelandic low, but not in the right position, which of course we know is not a bug, it's just that the atmosphere is not predictable. If we now make an average of all these cyclones, the result will be a cyclone, and much weaker, but not because of any under-forecasting of the intensity, but because of these position errors. So all it told us was that we are not forecasting the Icelandic low exactly where it is, but that was nothing new. But it appeared as something else. Here is, I was at a meeting in Stockholm University. An American talked about climate change or simulations of the atmosphere, and he had two different versions depending on some parameter he had run. He said he had got completely different results. And there was a lot of discussion about these completely different results. And I was sitting there and thought, aha, are they really different? Yes, that they are different, but are they randomly different? And then I found out that they are not. So take now a simplified, here we have a simplified version of the first experiment with negative anomalies. And here we are south of the equator. Sorry, the equator is here, so here you have some, yes, here you have North Pole, equator, and South Pole. So it's the first experiment with negative anomalies, and then you have the second simulation with positive anomalies, and it seems to be not related. But look now, what you can see now is that actually they are related. It's just a matter of a bias. So one is systematically colder or warmer than the other. So if we go back to these, if we add some temperature, constant temperature, to this picture, we more or less get the other one. Or we subtract something from this, and we will get that one. So the anomalies are actually highly correlated. And the difference is just more or less a plain bias. But still they appear as two completely different. So the difference in these two experiments was just that one solution was warmer and the other colder. Nothing more. So all these discussions about position and irregularities was just a deception. Then we have the availability effect. And I don't know how you make thunderstorm forecasts now, but when I was a young forecaster in the 70s, I noticed the following, that when we verified the thunderstorm forecast, those made in the afternoon for the next day's afternoon were much better than the ones we made in the morning the same day for the afternoon. And that is a bit strange because normally the longer the forecast, the worse, the shorter the forecast, the better. But here it was opposite. And this might be due to the availability effect. Because when we make the afternoon forecast for next day, we have already available observations of thunderstorms on the map. So it's highly available. But in the morning, when we sit down, at least in Sweden, there are no thunderstorms. It's rather hazy, might be stratus, and any thunderstorms are normally not available, neither on the map or on the radar. So we have to sort of imagine that they will form. As a consequence, we tend to under-forecast the thunderstorms, at least in those days. You might have more clever instrument or methods now, but in the 70s, we tend to under-forecast the thunderstorms just because they were not available when we made them. The primacy effect, and all this is sort of taken from Kahneman's and other books. So what I have done is to translate these books as much as possible into meteorology. And I hope to extend that in the future. The primacy effect is that it's very important, the first impression you have of a person you meet. It's a common saying. And the same seems to apply in meteorology, because if you receive 3 models in this order, the first one have rain, and the last one is dry. If you are victim to the primacy effect also in meteorology, you should judge the risk of rain higher than if you get them in this sequence. I don't know if this happens, but you can think about it. The first impression we tend to evaluate too much if all these forecasts are on average of equal standard. Then a very typical methodological feature, but also of course, we always want people to be consistent, not to change their mind, to have the same opinion today as they had yesterday. And in weather forecasting, we are all familiar with jumpiness. So when I was in the 80s at the European Center with Stefano and others, the only thing we could do was to correlate jumpiness with, or the skill of the forecast with the jumpiness. The more jumpiness, the less reliable, more steady, more reliable. But the correlations were very weak. And on the training courses in the 90s, we made tests. The participants they were given a lot of forecast, and they had to mark to what degree they were good or bad, jumpy or not jumpy. And then we saw the correlation. And this is the result for the different lead times. And it's more or less, when you look at it, it's more or less a correlation of plus minus 10%. That means no correlation at all for an experienced forecaster when it comes to it between jumpiness and skill. But the problem is of course, when the forecasts are steady, we have a warm feeling in our hearts. And when they are jumpy, we are sort of irritated. But when it comes to the final result, it didn't matter. So then we have a very peculiar, what we discovered at the Met Office. Now, here we have 3 consecutive forecasts from the same model. And the first one has rain. 12 hours later, the first one was sun. Next one is rain, and the last one is rain. And this is rather consistent, and we feel good. But the rain will occur in this sample. It's the Met Office model, but the same applies for the European model. About 60% probability of rain in this case. Then we have another case where it first rains, and then it's dry, and then it's forecast rain again. So this is very jumpy, inconsistent, and we don't trust the forecast and we are irritated. Still, the verifications, both for the Met Office model and for the European Center model, show that the risk of rain is actually slightly higher in this case, not lower. And how come? Now, first of all, we are deceived by our emotions. We want people around us to be consistent and not change their mind, and we are right. But we can't apply this moral standard to a computer, but we do. Secondly, we forget one thing which I hope you will not forget after this course, the rule of correlation. Because although these two forecasts support each other, they are quite near in time. And as you know, with numerical weather prediction, you have a first guess. You update the first guess. You make a forecast, but also a first guess to the next analysis. So all these are highly correlated, but of course these two are more correlated than that one and that one. And that plays a role in the second case, because now these two agree. And of course this one has, on average, the lowest skill. But they are less correlated. So the agreement here compensates, the correlation compensates the slightly lack of skill to make, on average, this statement as reliable as the first one. And you can think about this as if you want to know something and you ask an identical twin couple about something. What do you think about the EU? And these identical twins have the same opinion. Then you weight that hopefully less than if you just take two random people on the street and ask them what they think about the EU. If they have the same opinion, it weights higher because they are not correlated. And the same applies for, so we must think about the role of the correlation. You had a question or comment?
Yeah, just a little question.
Could you,
just a comment. When you were saying that in the first case you get 58% of risk, of rain risk, and in the second case it's more scrappy, so people feel less confident because, and then they based on some evaluation they get 63%. It is also true that sometimes when you do, I mean, it depends from the initial condition. If you are able on all the bunch of data to find some kind of principal component, then sometimes you do variation ordered along this kind of principal components. Then, in the first case, if you get, in the upper 3 simulation, for example, you get this behavior. I mean, I don't know how to explain, but if you act starting from a principal component, something which seems to be ordered inside all the bunch of data, and then you get these kind of things which are ordered, then it's rain, and then at some point you get this sunny, it is going to be less rainy, whatever. In the second case, if you move along the same order data.
could you put it closer to the mouth? Go.
Am I too close?
Yeah. I can't quite hear.
In the second case, when you order the data, you try to identify some kind of order, mental order also. But let's try to be more objective. Let's say kind of principal component in all the data you have on your disposal. Then you start to find moving, scanning, starting all these simulations with different initial conditions, ranging in some ordered way, and then you start finding these jumpy results. That maybe that can make a difference.
Well,
I don't know if
now we are it's a very important question because we have two things here. We have first a statistical result from the Met Office and from the European Centre, two different models, and they show the same effect. So when you, as a forecaster, are facing with this type of jumpiness, don't play down these forecasts because they are jumpy. So that is a statistical approach. Then we can discuss the physical background in the models about first guess, the autocorrelation, etc., etc. But first of all, that is very interesting, why this happens and why it is like that. But it doesn't change the fact. It's just that we discuss now at another level what is happening in the models. Because as I understand you, that you don't question the result of this. You just have good ideas about the deeper structures. That is very important, but it cannot be part of a forecaster's. He must make quick decisions. It's for scientists from this interesting result to find out the deeper reasons why jumpiness acts in this way. Is that? Yep. And then we have the confirmation bias. And that is, I have noticed both with myself and with others, that when we look at the EPS gram, we tend to, what we should do is to take only these EPS information into account, telling us the likelihood of rain. But what we do more or less unconsciously or consciously is to also look at the deterministic information which is put on the EPS gram. And I know when the EPS gram was started in the 1990s, Tim Palmer and I and some others didn't want to have this deterministic information at all in the EPS gram, because that would distract the use. But then it would be scientifically interesting for scientists to have this deterministic information together with the probabilistic. And of course that is a good point, but what it leads to is that we might have an approach that we start with the deterministic forecast. So here is now the Bologna, leading up to the Bologna snowfall. And then you can say, aha, here on Wednesday, the 4th of February, the control has 14 millimeter rain, but the operation model has only 1 millimeter. Which can we trust? And then go to the EPS to find out which of these two we should trust. And then some days later, it's the opposite. The operation model has a lot of rain and the control less. And then we say, aha, now it seems that the EPS is supporting one or the other. And that is, in my view, and also others, the wrong way to use EPS. The EPS should be used in its own right about the probability of rain, irrespective of the control or the state of art, because they are just two members, and even if you double their weight, they are 4 members compared to 50. But psychologically, that is how it works when they are on this diagram, that we tend to put the question, can we rely on the deterministic or the control, and use the EPS for that, which in my view is suboptimal. Unfortunately, very unfortunately, this was a whole rationale in 1992 for starting EPS. When EPS started, and I was there, so I know, the purpose was not to use the EPS as a forecast tool and not to get any probabilities. the TIC, the Technical Advisory Committee, was against us using probabilities from the EPS. They should be used from MOS systems. So the official rationale, let's see if I have that. So the official rationale from the ECWF with the EPS was that it should tell the forecasters if they could rely on the deterministic model or not. And this is scientifically misleading, suboptimal, because if the spread and the EPS tells anything about a deterministic forecast, it is about the ensemble mean. Just as the variance of 50 measurements tell you about the accuracy of the mean of those measurements, the spread of the EPS tells about the reliability of the ensemble mean or median. But for political reasons, perhaps ignorance or God knows what, the EPS started with a completely wrong scientific agenda. And it was only in 1995 that Tim Palmer, Bernard Strauss, and I, and some others, managed to convince the Center and the TIC that the EPS as such could be used as a good forecast tool, providing probabilities. But still, as now the EPS-gram is constructed, there is a clear tendency that the skill of the operation model becomes the issue, not what you can deduce from the probabilities. So my fourth point with the ECWF is that the rationale for starting the EPS was wrong, and that rationale is still living on. Because last time I talked to people at the European Center, it's still seen as a main topic, partly because the research people at ESA and NWF have the operation model as a dear baby. So it's much, the whole work is too much focused on the operation model and less the information from the EPS. It's more seen as the support to the deterministic model than a forecast tool in its own right. And then we have something called substitution. And that is another, coming back to this race about limits of predictability. And it is based on the 500 hectopascal forecast. And it's a matter of what you can read in these books. It's called substitution. It means that if you can't provide good results in one sector, you provide it in another sector. And then try to make it look like you are actually also good in the first sector. So there is a lot of concentration on the 500 millibar height, which is not bad. But equally or more important is, of course, the skill of the rainfall forecast, or temperature forecast, wind forecast, the real weather. But they are less much used as a measure of predictability. And as you saw from some of Roberto's diagram, it tends to level out. They still increase, but it seems to be level out. And of course, that is important. Does it mean that we have reached some sort of saturation level of the skill of rainfall forecast? And then, if the 500 is still going straight up, there is something to be understood. Because very few people, if any, have any interest in the 500-year potential. What we do at most is to look at the field, but the value as such has no specific interest. So again, the fifth point of ECWF mistakes is to put too much emphasis on the anomaly correlation of the 500 millibar as the most important thing to achieve. Thank you. Now, we come to some other pitfalls, and one is selective sampling, which I had a lot of problem with when I worked at the European Center. I mentioned it yesterday that we over-forecasted Portuguese cutoffs at day 5 because only half of them verified. We did not, it is true, half of them verified, but not because we were over-forecasting, because we got them in the wrong place or not at all. So by selective sampling, you might get the impression that things are under or over-forecast. And there are So here is you have this square with all possibilities, and then the number of weather forecast, weather features forecast and weather features observed should be the same for a good numerical model. The forecast, as I mentioned, should over-forecast in case these events are more dangerous. And then you have, in reality, so the forecast skill is this intersection between this forecast and observations. So here you have the perfect forecast. Then you can either say that since not all are verified, we over-forecast, but equally well, since not all observed are forecasted, we under-forecast. So if you make a selective sampling, you might reach a conclusion that we are both over and under forecasting at the same time, and we are neither. It is just a wrong application of conditional sampling. And then we come to this movie where she suspects that he is unfaithful because he is often late from work. And you who have watched the movie know that he is actually taking part in a dance. He's learning to dance and does that secretly. But now to apply a sort of Bayesian or statistical approach, we have now all husbands in New York. And then late from work, quite a lot of husbands are late from work, but only a small portion of them have affairs. So what she is confusing is the probability, if you have an affair, then you are likely, as you can see from this diagram, to be late from work. On the other hand, being late from work does not mean that be with the same high probability that you have an affair. And that is what is uneducated, in Bayesian statistics, uneducated wife confused. But it's also a common problem in other, we have the medical test. Paul is afraid that he has some fatal disease, cancer, HIV, or whatever. He goes to the doctor, and it affects 1% of the population. He goes to the doctor, and he's subjected to do a test which is, can you see, 90% accurate. That is true. It's 90% accurate. And he tests positive, and he goes home and hangs himself. And it was rather unnecessary, because if you now look at it again, a very small proportion of the population is ill. It's not a widespread disease. And then the test is 90% accurate in the sense that if you are ill, that is 90% likely that you will be recognized in this test. But it was interpreted the other way around, that if you test positive, it's 90% likely that you are ill. But as you can see from this diagram, it's only perhaps 10% likely. And the reason why the medical science is sort of over-forecast or overdoes it is because they want to take everybody as much as possible who is ill, plus a lot of other people, and then subject this smaller segment to more expensive tests to exclude those who are healthy and then recognize those who are ill. But this 90% accurate was sort of interpreted in the wrong direction, and as I mentioned, perhaps this was a problem in the early 90s in England. A lot of people went home and committed suicide, having been told that they are 90% likely to have HIV or cancer or whatever that scared them. Then we have the J Simpson, which you all remember, I think. Even if you are young, you remember the OJ. And the defense lawyer said that only one partner out of 2,500 who are beating their wives go on killing them. And that was taken seriously by the court and the jury, and he was acquitted. But again, it was the right answer to the wrong question. The point was not that the probability of wives being mishandled were then killed. The probability was rather to put, if a wife is killed, and obviously his wife was killed, what is the probability that it has been done by her husband, already beating her? So actually here we have murdered wives and wives beaten by their partner. And only a fraction are killed, but actually those who are killed, a majority of those are killed by their bad husbands. So the statistical question put rightly would have put J Simpson to the gallows or the gas chamber or whatever they do in California. So you see, it's both with the patient who hanged himself and J Simpson, your life might depend on if you understand statistics. Then we have the debate about gun in America, where it said that the gun lobby, only 1% of gun owners commit gun murders. And then we have the opponents who say that gun owners commit 90% of the murders. So this sounds completely yes. Losing my English as well. But this diagram shows the reason that we have a lot of gun owners, but very few actually kill people. But those who kill people are, to a large extent, gun owners. But in the public debate, these two arguments, which are completely consistent, are of course interpreted as one must be lying. They can't be true both. And then I have this. I have two children, and one is a boy. And what is the probability that the other one is a boy? And then people normally say, well, 50%, because boys and girls are supposed to be born equally much. And it's not true. So there are three ways to explain that. One is there are four possibilities: boy, 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 girl, girl, boy, and girl, girl. And since now I have a boy, the fourth one is not any possible, but there are three alternatives, out of which one has two boys, so the probability is 1/3 to have a boy. Or you can put it in a Venn diagram, where the first is 50-50, boy-girl, and since it's non-correlated, the arrival of boys and girls, it can also be called orthogonal. So the next is then orthogonal, and what you now have is only one square out of three where a boy figures at all. One square is excluded, it's two girls, but of the three where a boy figures, one has two boys. And then, to your pleasure, you can also apply Bayes' rule, the wonderful equation, and then we know that the probability of having two boys is 25%. So here we can fill that term, because now we look for the probability of having two boys already having one. That is to the left of the equal sign. Then the probability of having one boy if you have two is of course 100%, self-evident. And the probability of having a boy, probability of boy of two, yes, is 3, is a 20, is because only one case you have two girls, but you have at least one boy if you're in 75% of the cases. And all this simple mathematics leads to 33%. So there are three different ways to answer this problem, which normally we treat with our system 1. Our system 2 tells us this is a simple problem, so it goes to system 1 that just takes the first reaction.
Excuse me, Anders.
Yes?
May you return back to the previous slide? Today I don't understand. First, I don't understand because you have excluded girl, but you should also exclude...
You mean in this one?
Okay, but you should also exclude girl, boy, because you already know that the first is a...
No. If I had said my first child is a boy, what is the sex of the other one? That's 50%.
Okay.
I didn't say that. I said, I have a boy.
It's not the first.
No. It's very, yes, because if I say the first, then it's 50%. Or that chap there, that is my boy, but I have another child at home.
Yeah, but this is a trick.
It's a trick.
This is
Yeah.
Because if you ask yourself what is the probability to have another boy, it's obvious that...
Yes, but it's not only a trick, because here we have the Sally Clark tragedy, and where people confused, it was Sally Clark, and she had 2 children that died out of infant cot, sudden infant cot disease, and some professor came and said that the chance of having one is 70,000, and to have 2 is millions. And so obviously she had killed the babies. And she was jailed. And later she was released because, first of all, there is a correlation. This infant cot disease is sort of correlated. So some families might be more affected than others. So the probability of 70,000 could be reduced. But the problem was wrongly posed. It should be posed as, if now 2 children die, and we know that 2 children have died, or 2 babies have died, what is a likely cause? And then from statistics, we know how many are died by disease and how many are died by being killed. And that was in favor of Sally Clark, and she was released, but unfortunately then was so depressed, so she committed suicide. So, and it's the same you have with the chance that you will win the Italian lottery twice is very small, unfortunately. But that somebody in Italy will do it is significantly higher, because we have not specified any individual event. And the same as I said on the coffee break, if I come into you and say, I had a fantastic experience, it only happens 1 in 10 million. I saw a car with the registration number BO1468911. Nobody is impressed. But if I say I go out now and see if the first car that comes has registration number BO146658881, then I go out and come back. The first car had that number. That, of course, is a sensation. It's 1 chance in 10 million or whatever. So it's very important how you specify the problem.
One problem that, to me, it's also not well posed in statistical terms is when we compute the returning period of a certain event at a certain location. For example, precipitation exceeding 100 millimeters, then you do the statistics. But this is exactly this point. I mean, because you compute the thing exactly at this particular point. But if you enlarge a little bit and you take into account that it can happen even 20 meters away or 1 kilometer away from your position, then I think you get a total different.
Well, if you the return period of heavy snowfall in Bologna is one thing. The return period for heavy snowfall in Emilia-Romagna is a different thing. So,
we try to confuse often this concept and say, okay, if the return period is 100 years, that means that I will be safe without taking in account that this is a sort
yes,
of,
yes. But and then also another problem is that the more extreme the feature is, which the return per period is supposed to cover, then the less data you have in the history. So then it might be very unstable calculations. So then we come into Bayesianism, and that was the topic for Wednesday's lecture, so I cannot. Then we have interpreting, now I jump a bit, because the anomaly correlation, which is very popular as a measure of skill, also has some deceptive characteristics. So here we have two cases when the anomaly correlation is 0, because all the values scatter around randomly in a circle around the reference point. So there is no correlation. However, the error is much smaller in the first case than in the second case. And it happened that the Swedish monthly forecast system was evaluated only in anomaly correlation terms. So it looked as if it had not much skill, but it just because the atmosphere was very close to the normal state, so the scattering was very close to the origin. So the errors were small, and the RMSE was small, but they never measured the RMSE just from the anomaly correlation and got the wrong impression. And that's why at the European Center we have both anomaly correlation and root mean square, because they show different things. And also another factor, if you in one season have a low anomaly correlation, you have one spring, low anomaly correlation, the left-hand curve. Then next year, the same spring, you have again a low anomaly correlation. But then if you want to increase the samples, you say, now I have the anomaly correlation for 2 consecutive springs. Then you put them together into the right hand, and suddenly you get an enormous correlation. Just because the 2 years differ in the general patterns. So be aware of that you can artificially, not manipulate, but you can actually get quite strange results just by combining data in a normal way. So 1 year low skill, next year low skill, but together they have high skill. You have the same effect if you, yes, so I'll leave that. And then we have what I mentioned the other day. You can actually improve your anomaly correlation by changing the climate. Or rather, as happened at the European Center in the 80s, we had an American climate, the NMC climate, for our anomaly correlation. But then we were able to compute our own climate based on later data. So here is now the anomaly correlation from a climate in the blue line of some 1960-90 standard. And then we have the observations up there, and the angle is small, so the cosine of the angle is high, the anomaly correlation is high. But then we change the climate to a more modern one. That means, of course, that now this climate comes closer to the observations. And doing that, the angle will increase, and the anomaly correlation go down. So if you improve the climate reference, you are likely to see that the anomaly correlation goes down, because previously part of the skill was the ability of your system to identify that it's warmer or colder now than in the previous reference period. And alternatively, if you want to cheat, you take an old climate and make the computations, and you improve your anomaly correlation, and you don't tell anything, so you have not lied. It is up to the reviewers of the paper or the readers to find out that, aha, this improvement is not due to any improvement of the model, it's because he has used an outdated climate. So you see, statistics never lie. Human lies. Thank you. So, one problem in all this is our tendency that from random data create images, patterns. And most famously, we do that on the sky, on the starry sky, where we create all kind of animals or gods. Another is our, and I had not mentioned that because it sort of has been a part of the statistical education for decades, 100 years, not to draw conclusions from too small samples. And if you do, be careful about the uncertainties, like you are in the Bayesian approach. Then you have the Stratsky-Joule effect, which creates convincing looking periodicities from random data. And then you have the lethal regression to the mean effect, which is the main topic for this. And here is now a report from Meteo France to the user meeting in 2011. And what they saw, or think they saw, was actually very important. Here is now the 15-day ECWF forecast, and this is now the mean error. It's the mean error of the model and the mean error of their statistical interpretation, which should remove any systematic errors. And as you can see, it does so for the short range. There is no mean error, practically. But then in both cases, after 5 days, both systems develop a very strong systematic error of one almost 2 degrees. And as you know, we all want models, in particular to use in climate research, but also for monthly forecast, seasonal forecast, not to change their characteristics, not to get wetter with time, or cooler or warmer with time. They should have a stable model climate. So now if the ECWF model developed a 2-degree mean error in 15 days, it was a real serious systematic error with the model. And the reactions in the ECWF, where I was at the time, was sort of mixed. Some were, of course, upset or concerned, and others were happy because now they had a problem to solve. And then I came and said, no, I don't think there is a problem at all. There is no problem at all. And the reason is that this month was 2 degrees, 1.5 degrees warmer than normal. It was February 2011, and February 2011 in France was about 1.5 degrees warmer than normal. So what you see here is actually skillful forecast with some bias, but that's a no big. So what you see here, if you now take this, that in the short range there is no problem. And then the problem comes because the longer the forecast, the less skill, more non-systematic errors. And it means that the forecast more and more, instead of scatter around the current state of 1.5 degrees warmer than normal, more and more start to scatter around the climate, the moderate climate. As you know, forecasts going for very long are supposed to approach the climate. So when you want to know the weather in 78 days, the best you can say is the climate average. So now, since it was an anomaly by 1.5 degrees, due to non-systematic errors, the butterfly effect, our inability to make perfect forecast, non-systematic problems, the mean error gradually went down to 1.5 degrees, exactly the value of the anomaly for February 2011. So a lot of people were disappointed at the European Centre. There was no problem. The only problem was that we don't make perfect 15-day forecasts. But we are working on that, of course. And then, about the same time in April 2011, I got a feedback from the Met Office. I've been employed there for 2 years to remove mean errors or systematic errors from the forecast. And now they had found that there was a mean error developing. So here is a mean error, and depending on the time of day, is larger or smaller. So that's not the problem. The problem is a gradual drift to cooler and cooler temperatures, as if there was a model drift. And why doesn't my Kalman filter take this away? Had they paid me unnecessarily? Again, April 2000, or was it, yes, 2000, sorry, it was 2012 perhaps. Anyhow, this month, April or March, was the warmest since a long time. So this month was unusually warm. And we have the same effect now. The forecast, due to non-systematic increasing errors, cluster more and more around the model climate, which is almost the real climate, and that is seen as an increase of a mean error just because the verification period is on average 2 degrees warmer than normal. So there was no problem here either. But not everybody at the Met Office was convinced, so they made a test, and then they had random numbers, and then they computed the errors. So they treated this as forecast and verification. And then they computed the forecast errors and found that these appeared systematic. But there is no systematicity. It is just a statistical effect. It looks systematic, but it's still random. And I don't know if I mentioned it, but for example, I can present myself as an expert on seasonal forecast for Bologna. So I can go to the newspaper and say that the 13th of February 2016 will be, let's say, 3 degrees warmer than today. Then in 1 week's time, I will come and say, well, the 20th of February 2016 will be 1 degree cooler than today. Then keep on for every day of the year to give a trend forecast, a 365-day trend forecast for Bologna. And at the end of the year, I will publish a scatter diagram with my forecasted trend and the observed change over 365 days. And to your amazement, it will be a very nice correlation that will score about 71% in correlation. And it looks as if I can forecast the temperature in Bologna 1 year ahead. Of course, I can't. What I do, I know the climate of Bologna. And if it's today is 3 degrees cooler than normal, what I say is that next year is likely to be 3 degrees warmer. So all I do is just to give the climatological average for Bologna, but not directly as a difference between today's weather and the climate. So it looks smarter, but it's just the climate statistics I use, the typical temperature for Bologna in 1 year's time. But to present it in this way, make it look like 71% correlation skill to forecast the temperature on the day 1 year ahead. And here is another. So what happens is that during a heat wave where you have a sort of constant anomaly, the forecast, of course, catch that, and there is no problem. But then when the systematic errors increase, instead of scattering around the true value, it started to scatter more and more around the climatological average. So the climatological average is this thin line, and the mean of all the forecasts is this thick line, and it is sort of then constantly cooler than this persisting warm anomaly. Because forecasting persistence is as difficult as forecasting changes. Then, now I have talking about the negative things with regression to the mean. But it also has a positive side. And I was told when I was a young forecaster about an early morning, the chief forecaster came up at 4 o'clock, 4 or 5 o'clock, and the young meteorologist was standing there, the telephones were ringing. What had happened was that when they went down for the night to have a sleep, it looked like it would be a nice day, sunshine, no rain. And when they come up, there is heavy rain outside. And the chief forecaster hasn't got a clue what has happened. He hasn't had time to look at the map. There was no radar at the time. But he assumes that one of those thunderstorms that were prevalent the day before had not yet died out. And it had drifted into Stockholm, where we then were. So it was just a coincidence, bad luck, that one of the thunderstorms were still awake. So then he told the young forecaster with the telephone, tell them that it will soon die out. He hadn't got a clue what was happening, but he applied regression to the mean. It can't get worse. It can only get better. As the first, then he started to look at the maps and perhaps came to some other conclusion. But the first reaction, the first fast thinking was to apply regression to the mean. And also when I was at the airport in the 1970s, and we were suddenly attacked by unexpected thunderstorms or fog or whatever, and we hadn't got a clue where it came from and how long it would last, then we had to issue a 2-hour forecast, a trend forecast. And that had to be done immediately, not after 2 hours. So we then put gradually everything will be fine. And then when we perhaps looked and got in more information, that might then change half an hour later. But so we are actually using this regression to the mean also in our favor, that it can't get worse, it can only get better. And then we make use of depending now on the weather system, if it's it is the same when in the past when the numerical weather prediction was not as good as it is now, we could also apply it on a large scale. A cold outbreak couldn't last for long. A heat wave had to end after 3 or 4 days, and we made use out of the relation between the scale of the feature and the typical predictability. So we made use of the regression to the mean effect in our own interest. The father of the regression to the mean effect is a cousin to Darwin, Francis Galton. And he had noticed that sons of long fathers were also long, but not as long. And sons of short fathers were also short, but not as short. So both sons regressed towards the average height of a man. And it's from this man and that sort of completely non-methodological application that we have the word regression to the mean. So here is now how I forecast the weather 1 year ahead. So we can, so what I do here is now for Heathrow, the temperature for May 1 year on the x-axis, and then the temperature for May the next year on the y-axis. As you see, there is no correlation. But if I instead plot the difference, still the current year's temperature, and then the difference to the next year, then you have a clear correlation. But it's still as random, but it doesn't look random. And this can be explained also from my use of geometry. So this 45-degree angle is the change of the year, and the anomaly, the correlation is a cosine of 45 degree, and the cosine of 45 degree is 71%, upon 71. Or you could say here is a circle, and you have numbers around the circle, and there is no correlation because there is no structure. But if you now, instead of this equation, you compute the difference, then suddenly you have an ellipse, elongated ellipse, and the axis through the ellipse, I think we come up. So now you have a correlation, you have a structure, you have a correlation, and it turns out to be, again, 71%, or 1 over square root of 2. But it's still random. Then to come back to how we make use of it, so here is now a typical EPS-gram 15 days ahead. And you see there is a warming and then there is a cooling, both in the daytime temperature and the nighttime temperature. And I know that 1/3 of this is to the right, is mainly due to the regression to the mean effect. And I will explain that, because if we now use this clickable EFI map, you can click, you can get the model climate. So now we have the same forecast for Barcelona, but now with the underlying model climate. And that enables you to see that this decrease in temperature is because it has been anonymously warm in the beginning, and now it's sort of returning regression to the mean because lack of skill. It scatters around the model climate, and it can blow it up. So you see that not only the mean values agree with the mean climate, also the spread is approximately the same as the climatological spread. So it means there is no information apart from the climatological information in the last third of this 15-day forecast.
Question about that. This is similar to what you showed before about the warmest, a warm month in France, in some sense.
Yes.
So you are saying that in the, let's say, if we have a month forecast, in the last part of this forecast, the model tends to reach its mean, then its climate. But then I have some difficulties to understand how could the seasonal forecast be done, because if this was true, this means that after time...
David, no problem. This is one example. This is one example for Barcelona in 2012. If this had been a typical, or then of course there would be no skill in any forecast from the European Center after 12 days. And the reason why we have skill in the monthly forecast 2 or 3 weeks ahead, and even in the seasonal forecast, is because there are cases, as I will show, when this does not happen, when it actually, yes, it goes down, there is a regression to the mean effect, but still either the mean stays away from the climate mean, so there is a signal, or if it agrees with the climate mean, the spread is smaller. So, I mean, there is no reason not to have sometimes the weather agree with the climate, but since the spread is smaller than the climatological spread, we can trust that this forecast actually is more likely than just a climatological statement. So it is just a pedagogical example to show regression to the mean. So please trust the forecast system beyond 12 days. So here is now 4 typical epsogram, an epsogram with 3 days interval. And they show ups and downs, warmer and cooler, and increasing uncertainty. But it means slightly different things depending on if you are in the early stage or in the later stage. So here is now the evolution along the median. Warmer, then colder, and then warmer again. And also you have a uncertainty increasing. And now here is now the climate. So the whole system converges towards the climate on day 12 or later, as we normally expect it to do, at least in this pedagogical example. And so the warming in the first period is because of atmospheric processes, advection of warm air, warm fronts, whatever, as we. Then the warming in the second part is due to the regression to the mean effect, because on day 9 the forecast is unusually cold, but still with large spread. And then when the skill goes down, it sort of goes towards the climate for statistical reasons. And by the way, I would also like to tell you that, which I do in the user guide, but I forgot to tell it here, that the relevance, so the relevance of these, so here it disagrees. You'll remember the climate is somewhere higher up. So here you have information, both because the mean is different from the climatological mean and the spread is small. Here the mean agrees with the climate, but the spread is much smaller than the climate. So this is also valuable, relevant information. Here the spread agrees with the climatological spread, large spread, but the median is away from the climatological mean. So again, we have useful information. It is uncertain, but its average is far away from the climate. It still provides a valuable information. However, in the last case, which has the same spread as this one, but the mean now coincides with the climatological mean, then there is nothing to gain compared to just a climatological statement. So it's an interplay between spread and the mean that decides if there is a predictable information or not.
So Anders will think that it is useless to plot meteograms below the time.
No. No. Have I said anything? No. No. I have no problem with meteograms. I mean, we have no meteograms on the clickable EFI maps up to 15 days. And if you look at those, you will see that it quite frequently happens that you have a signal all the way to day 15, either because of the spread or the mean or in both. So, but what this tells us is that we can ourselves, by looking at this 15-day EPS-gram, see how long we can trust this particular forecast. It is 15 days, but sometimes we can only trust it perhaps for 10 days, because then the mean and the spread coincides with the model climate. And sometimes we can see that it is not even the case on day 15. It might happen on day 18, so we can then, in some sense, say that we can make useful information even up to day 15.
This means that it would be very useful to plot, or at least to keep in evidence the climate of the model, and to start to be suspicious when you see that you are converging.
Yes, and that is what, I mean, I have been critical about ECNWF, but I am also positive about many other things. And the one very positive thing is this clickable EFI map, where you can get the climate in the background and then actually yourself see if there is relevant predictable information up to day 7, 11, 15, or even longer.
Because of course there is a variation day by day, in the sense that mode, the median, or the spread, is because you have completely lost the forcing that you got at the initial stage that bring you away from the normal behavior of the model.
Yes.
So, and that in that case you have lost and you are going towards.
So remember that the coolings and warmings in the later half of the 50-day forecast is not totally, but mainly due to a statistical effect. Before the first half is mainly due to methodological, physical, but also an element, of course, of a regression to the mean is from the very start, but very small, but it increases in time because of the increase of the non-systematic errors.
Yes, exactly this I was trying to show in this monthly meteogram that I had on my presentation, where you see the plume that goes up and down and then tends to agree with the climate towards the end. So the attempt was to measure this, the time when the regression to the mean starts. And I think now I have an idea how to measure that and then highlight it on the graph, so you can choose. You have to be careful on the side of the graph when this regression to the mean.
Then in the 1980s, when I was at the European Center with Stefano Tib, and there was no ensemble forecasting, it was just deterministic, we suddenly came into and it was just 10 days. It happened sometimes that there was a return of skill. So we could see in the verifications that the forecast became completely useless on day 7, but then on day 8, 9, and 10 came back. And it once happened when they ran a 100-day integration that the forecast on day 38 was perfect. So you will also see that, I think, in how these conditions about spread and skill coincide with the climate happens somewhere on day 12, but then strangely there seems to be skill coming back the last days. And be careful. It might be coincidence. There might be some sort of return of skill, but don't jump to any conclusions immediately. But keep it under watch. So now if you have a meteogram, you have different things. Here, a deterministic interpretation of a deterministic forecast. It's always physical processes. You can always see the Bergen School model verified. But if you have an EPS-gram, you start with physical, methodological explanations, but then gradually it becomes more diffuse. It might be a high pressure or an anticyclone, and then you come into the later 1/3, and then you cannot really explain it in terms of synoptics because it can be a lot of things. It's more a statistical effect. So our ability to explain changed from physical in the short range to statistical in the later stages. So you will, and then finally, there might be a regression from the mean effect, as I call it. And I became aware of that in the December 1999, when this devastating French storm, the 26th of December, hit France and Germany and Central Europe. And it was not perfectly forecast. It was not very well forecast. So there was a lot of complaints in the media. And then some days later, a new wave, a new cyclone turned up in the Atlantic, and Meteo France issued a warning about severe gale or hurricane winds or whatever, and it verified. There was a second storm in a short period of time. One was called Lothar and Martin. And then there was a lot of talk about it was thanks to Meteo France new model or the European Center model and the experience of the forecast, all kind of meteorological explanations. But I was in France at the time, so I took the forecaster aside and said, well, whoever his name was, when I was at the airport and we missed one severe thunderstorm. Next time something that turned up that looked like a thunderstorm, we went for it. Because missing one thunderstorm is bad enough, but missing two is a catastrophe. So just to be on the safe side, we just went for a thunderstorm the second time to over forecast. And he smiled and said, well, that is also what we did. So irrespective of the new model or whatever, this second wave coming up 3 days after the first one had to be forecasted as a devastating storm, whatever the synoptic indications were, because it would have been a political disaster to miss 2 severe storms in a row. And I call that regression from the mean effect. And here are the maps. And I'm happy that Meteo France succeeded, but I don't believe in all these scientific explanations why they succeeded. It is just a common forecaster thumb rule. Don't miss 2 severe events in a row. Over forecast a second. Thank you. Okay. So summing up the course. The first day was about classical probability, but I started to talk about the role of the forecaster, how he can add value, not by questioning the physics behind the -4 degree forecast, but to question the forecast about the clouds clearing. And depending on how likely the clouds are to clear, he can modify this -4 to 0 degrees on average, to a few degrees below 0, just to at least tell people that there might be frost, but perhaps not -4. And then finally, the third one is to tell him in probabilistic, in other terms, about the probability of it staying overcast and +2 or clear and -4. So that is, I think, increasingly the role of the forecaster to brief the community. Then next day, it was about the power of randomness, the power of randomness. And then I showed this Slutsky-Joule that looks like a climate series with an unexpected decrease of temperature during between the Napoleonic Wars and the Crimean War. But it was just an effect of randomness that when you make running averages, the Slutsky-Joule effect induces periodicities that are completely random, but might look very physical, very convincing, but has no meaning whatsoever. And that we should be on the watch out for that when we see statistics with running averages. They, of course, might not be wrong, but the Slutsky-Joule effect might still play tricks with us. Then the third one was about how to add probabilities, since that had been a problem both in Sweden and the European Center, and people seem to underestimate the problems doing that. And I showed some examples where it can be easily done when the probabilities in 2 periods are exclusive, one or the other, or when they are non-correlated. Then it can be done. When it's correlated, it can in principle not be done easily. But I suggested that some easy tricks to not get too far away from the truth, and also this type of diagram where you can put in the probabilities and then see how much they overlap from your assessment of the synoptic situation, and then easily draw the conclusion about the probability of rain at all, the full green range, or persistent rain. It means rain in both periods. And then the last on Monday was this my baby, the Markov chain. And that first looked like a simple contingency table with yes and no, rain or no rain. But then if you play a lot of mathematical tricks, you can expand it into interesting terms, where the first one is let's see now, it's the persistence, the degree of persistence. The second one is the climate probabilities. This is the variability of the system, and this is a time folding factor, how long this variability will contribute to variability in the total system. Tuesday was about averages, the problem with computing means and the problem of interpreting means, which is underestimated. It's easy to understand often what the mean means, but it's difficult to compute. It can be median, mode, or average. Whereas probabilities are easy to compute, but perhaps difficult to understand. However, this case with using mean values in so-called bimodal situations is a matter of controversy in the methodological community. But with this example, where there is a 50-50 option for going north or south of the UK on its way out, actually what the routing forecasters do, they send the ship along the ensemble mean towards Newcastle, not to get aground in Newcastle, but to wait for later forecast, which they then can more easily adjust to when they are in the central course. So the ensemble mean, in my view, is still a useful way to do deterministic forecasting. And then next one was about verification of probabilistic forecast. And there are some mathematical ways. One is a copy of how we analyze the root mean square error. That was my favorite. There is another one by Alan Murphy, a guru in the verification science, which I quite don't understand, to be honest. So, but it is there, and I think this PDF by the lady who is ill, yes, it's very good. So I recommend that to get a better understanding of Alan Murphy's verification and decomposition than I can provide. However, for many purposes, it's just enough to plot the reliability diagrams. And then just looking at the reliability diagrams, you can see if the forecast is reliable, if it's along the 45-degree lines, if the forecasts are sharp, meaning that they are less around the climatological mean and more towards lower probabilities or higher probabilities. Then you can also easily see if the so-called resolution is high or low. So plotting the data might actually be as informative as computing the mathematics of the terms. And then I explained why the Breyer score has an ability to punish you if you, as a reliable probabilistic forecaster, puts a probability that you do not quite agree with. But you do that's for different tactical or political reasons, but the Breyer score will punish you for that. And it sounds a bit metaphysical, but I explained why that happens. Then I also talked about, in understanding deterministic verification, how the scores, like the root mean square error, depends not only on the accuracy, how close we are, but also to the variability of the model. And here is an example where actually a good model should have higher error because it's sort of a realistic simulation of the atmosphere, giving the full variability. Whereas a bad model, which is constrained because of bad physics, poor numerics, coarse grid, is not able to simulate the atmosphere equally well, will actually turn out to score better. Lower RMSE, because it will not take chances as much as the realistic model. However, the difference between bad and good shows up in the variability. The good model has a constant static model climate, where the day 10 forecast looks like a typical weather map as a day 1 forecast. Whereas at the bad model, the forecast coming out with increasing forecast time, looks more and more unrealistic, perhaps smooth or in some way not typical of the atmosphere. And then the Bayesianism, how you have a certain, as a forecaster, you have a certain idea about the most likely evolution, and you keep in mind it can be colder, wetter, drier, or colder, so you have some tolerance, but you have some favored opinion. And then comes new information. It can be an ECNWF forecast, it can be observations, something comes in, and then you adjust. If you think that it needs to be adjusted, you adjust your opinion with respect to this new information. And all this is sort of formally handled by the Bayesian mathematics. And here's my favorite way to explain the Bayesian, how he had a billiard table, stood with the back and threw a ball in the table, and somebody drew a chalk line, a white chalk line, and then he threw repeatedly balls after the other, and after every throw he was told if it was to the left and to the right, only that, and from that information only he was able to gradually or immediately come up with probabilities where the white line was. And the more balls, the more accurate became this evaluation about the white line. So this is, and then one way to apply this, some of the concepts like this Laplace Rule, where if you have a limited number of ensemble members, you can add 2 extra members, one with rain and one without rain. And the point is to avoid the situation where you have either 0 or 100% probabilities, because they cannot really be 100 or 0 if you have a limited number of members. So it prevents you from ending up with 0 or 100. And I also showed how you can, if you have now just one member in the first period having rain, that the next period, whether it's rain or not, should not be entirely decided by this very model, because that would give either 100% for rain or 100% for dry. But including these sort of extra Laplacian members, you will sort of soften up. And for example, if there is now rain in the first period, forecasted only by one member, the relevant probability for the next period is not 100 or 0. It might be, for example, 25%. Well, you can say 40 or 15. That's not the point, but it is not 0 or 100, and it's about perhaps a realistic level. Another application of the Bayesian approach is the Kalman filter, which in some sense is like regression, but while a linear regression. But while the linear regression gets a sloping line, a relation between forecast and observation, that is once for all given. Having the data over 3 or 4 years defines the relation and the uncertainty, full stop. The Kalman filter works on a day-by-day basis. So it starts with some assumption from previous calculations, a new verification enters, and the Kalman filter as a Bayesian system takes impression of this, and depending on if the observation is close to the y-axis or far away, it will either translate, that means mainly changing A in the equation, or rotate, mainly changing B if the observation is far away. The decision is made from what is the least effort, and it's easier to translate close to the y-axis, easier to rotate if it's far from the y-axis. And then perhaps the most important one, here is the forecast matrix, skillful, 2/3 of the forecasts are skillful, and of the rain forecasts are skillful, totally 80%, but mainly then thanks to it's easier to forecast dry conditions. And then we assume that 40% of the forecasts are uncertain. And just to push the argument, no forecast is issued. And then we show that this was actually beneficial. Those who were sensitive to rain took this absence of forecast as if it was going to rain. Those who had high costs for protection found it favorable to interpret a no forecast existence as there will be no rain. And this actually added to the value of this rather skillful system in the first place. So by admitting just that I don't know, full stop, added the value to the forecast. And then if it could then be further telling about almost certain or very uncertain and anything in between would further increase the value. And then I put the numbers from 80 to 20% on this only sort of verbal. So it also shows that you don't really have to use probabilities. It's just enough to tell verbally if you are uncertain. It's good enough. Then having probabilities will, of course, further increase the value. But already admitting uncertainty and then only in verbal terms will highly improve the forecast service. And then we have, all this was based on the cost-loss model, where the more money you have, the happier you are, and the less money you have, the more unhappy you are, in a linear way. But as science or research have shown, people do not normally react that way. So here is a summary of Kahneman's main result, that to get money increasingly does not increase our happiness in the same degree, and we tend to, when we have a chance to gain money, or lose money, we act differently. We avoid risks with the gaining money. We rather prefer to have 700 euros in the hand than a chance of gamble 80% for getting 1,000 euros. So we rather keep the safe option. On the other hand, if we risk losing money, we are more open for gambling to take the chance to avoid any loss at all. And that's why the curve is sort of S-shaped instead of a straight line. And I think that if I had been half the age I am, I would devote the rest of my methodological career to explore this model, how it would affect the methodological cost-loss mathematics. And then from this mathematics to how it actually is done practically. And I showed one example from the BBC Met Office in December 2011, where these very skillful people still hadn't got a clue about the weather because it was very unpredictable. But still, by avoiding the normal pitfalls and making use of this concept to admit uncertainty, which they did, but not in a way that made them look foolish. On the contrary, they first of all gave good service and also appeared very professional. So instead now this Carol Kirkwood, instead of blaming the computers for being jumpy, which they were, she said that the cyclone has changed track and we are revising our calculations, which is actually rubbish, but it's sort of not totally rubbish because we means that the supercomputer in Exeter were running and the cyclone has not changed track, but the extrapolation of the track is different. But it doesn't matter, because the point was to tell people we are uncertain, but in a professional way. And they were much acclaimed, which I can self-confirm. And then, again, if you, by combining, like the astronomers in the 300 years ago or 200 years ago learned, is by combining observations, or in our case, combining forecast, that we increase the accuracy, not by selecting what we think is the best observation or the best forecast. So here is just, it's not even ensemble, it's a 3 or 4 member ensemble of the last runs of the Met Office model or the ECNWF model. I don't remember which one, it doesn't matter. The dashed line, the gray dashed line, shows the error for a 5-day forecast. And the full gray line shows the error when the last 3 or 4 forecasts have been combined, weighted together. And you see a modest but significant improvement. Surprisingly, the jumpiness, the red dashed line, goes down dramatically. And since many people in the public identify jumpiness as bad forecast, by combining forecast in the lagged mode or in the ensemble, into the ensemble mean, the forecast will be slightly better, but above all, much more steady, so that they will give an impression of having become much better. So in this case, you get a feeling of forecast improvement completely for free. Then what I showed today about that the EPS is a forecast tool in its own right. And of course it can be used to judge the quality of the deterministic models, but that is not mathematically operationally consistent, and it's not how it should be operationally used in my view. And then I told you about how husbands and wives should be educated in probability theory, so they draw the right conclusions about things. And here is how Météo France triggered the alarm unnecessarily. And there have been more examples when I've been traveling around, where people have spent 1 or 2 years investigating systematic errors in the Met Office model or in the European model and God knows what, and found these sort of mean errors increasing with time, and thought that, aha, here is a problem, where it in most cases have been the regression to the mean effect. And finally, when I was young, in the 60s, a young forecaster, the dark clouds threatening my existence was the arrival of numerical weather prediction. The computer was seen as a threat. And I feel today, in particular among modelers, NWP modelers, at the European Center, perhaps in Bologna, I don't know, at the Met Office, the dark clouds that is threatening the modeler is the arrival of statistics that is threatening his world view. So that's my final picture. Thank you.